Okay, great. Okay, so I'm back and I'll tell you about a completely different project, which is not really related to necessarily fun, like traditional methods of robotics, but you can probably think of it also as material robotics, and is like a follow-up of a lot of research that I did previous in my career that's now been adapted to materials from the Pacific Northwest region and new geometries. I know it's getting a little bit late and it's after lunch, so this is my team having fun on this project. And what you should also maybe note here is that some of them only need one hand to hold up this building component. We'll get to that a bit later, but this is a project that we have a small ARS funding grant for, but we've also managed to get some fellowship funding from the College of Design, and we've also had really great support from TallWood in general and the staff at Emerson Lab to kind of go above and beyond what the original scope of the project was. We also have emotional support from the PDX Llama that visited us to the students' happiness. But if we get a bit more serious, so this project really like had the aim of trying to see two different things. So one, if we could make deployable building components that use the hygromorphic properties of wood through drying to create shapes so that they could be flat packed and then curve up or out into more stable shapes. And then secondly, to see how we could use really thin materials to make stable structures in architecture and therefore keeping them incredibly light. And when we looked at, this is something that I've been doing for a while, but usually with sawn timber. And of course, as many of you know, when we look at waste products that come out of this and material efficiency, peeled veneer is often seen as like a solution, especially for small logs. And so when I first came here to Oregon, one of the first places I went was to Ferris and saw this peeling process and the veneer, and I had never worked with anything like this, but it sort of begged the question to me that like if we if we peel the wood and that's really great, then like how can we put it back together into slightly more efficient forms than just stacking it up? And also that I knew from my work with wood scientists in the past that peeled veneer is completely tangential in orientation, and which means it has a huge swelling and shrinking coefficient, which is like kind of like the superpower behind the self-shaping. So this is like the sort of the underlying idea that like rather than taking the whole cross section of the tree, now with our new methods of manufacture and computation, how can we like put it back together to give it new functionality? And basically, how can we make like many strong tubes out of one tree rather than using just that one tree? And again, this sort of deployability is something that I studied in the past, also at large scale. But here we apply it really in a different way that I think is actually even more exciting. So the way it works is pretty simple. We get these peeled veneer sheets, and we actually did get some that were green and undried in this case, which is something we've never tested before. But if they've been dried already, we hydrate them so that they expand. They get wide, and then we glue them together, like cross-laminated with a thin hardwood layer on the outside that's also peeled. And then once they're flat, then we press them with the hydraulic press, and then they shape up through drying. So this is like one in our students' apartment that works. And so we did this with a series of studies like at a smaller scale, looking at like what diameter we get and what variation in curvature we get. And we also, thanks to working also with Erica Fisher, we were able to do some initial compression testing of these tubes. And our student and us, we published this and presented it at WCTE in Brisbane in June. So you can look up the paper for more information on that. But then more in line with the manufacturing side of the project, we also wanted to look at how we could really do this with like standard veneer sheets. And so we manufactured like a number of sets of tubes. We modified the PUR rig at Emerson for doing bigger panels so we can do this faster. So we take the sheets, we record the veneer, the orientation in the veneer, which we'll talk about later, and then we glue them together. It's like almost like a factory. And then we stack them in here, and we can stack like basically as many in here in one press because they're super thin and flat as we can glue in time. So like in theory, we could actually fill up the whole press and press like an entire project in one go of tubes in one go, but we can't glue that quickly yet. And then after that, we have to dry them out. So when the first round of production that we did that actually in my lab in UO because it has unlimited heat from the steam plant. And so we just turned the heat on, and unfortunately to Braden's demise, who had to work there in the winter, we just turned the heat on and turned it into a big drying chamber. So we dry them out, and they start completely flat like the sheets there. I also transported them on top of my Subaru, so like it's like small scale production but big output. And then they slowly curve up over a couple of days, and you can see that on the right hand side. So they're curling up into like this sort of cinnamon stick geometry, and then on the top is one that's like has finished already. And then we milled the ends of these out with the Roa to give them a little bit more detailing, and we developed a sort of solid timber connection, or actually veneer laminated timber connection for like how to like resolve these sort of slightly wonky tubes to connect to each other. And we built these up into like a demonstrator structure that many of you probably also saw at the Mass Timber Conference. And again, like I just want to highlight, like this is also Braden, but they're huge building components and they weigh very little. Also demonstrated by Mark Fretz and some of our students at Pickathon. And I like noted, like, look, they're like not even trying. It's amazing. But in like all seriousness, I think it's this we built this demonstrator structure to show that this is really lightweight, but like this demonstrates it quite well. So we have the base of the structure. It's like 2,200 pound MPP plates that Ferris very nicely donated to us. And like this is the maximum you can carry on this truck, but like our actual structure is like just like hanging out there at the top. And then like when we get on site, for example, and we installed this inside at the conference and also at Pickathon over the summer. And it's like really amazing because just with like very little equipment and just people, we can assemble it like on the floor into these, and then we need to do a little bit of lifting and then lift it all up in one go. But the whole structure is like less than 500 pounds. And that includes all of the connectors. So when you start thinking about like also efficiency on site, it's like the lightweight is good for structures, but it's really amazing how fast these things can come together when people can just lift them up. This is the completed structure like back in the lab, and we've assembled it like 3 or 4 times now. And it still goes together really nicely. So also one of the interesting findings from installing it at Pickathon was that like it comes together like there's a lot of, I think, Brad, you were also at Pickathon installing some things, and like it's very much into sustainability and low impact. Like our team of like 3 students and Mark Fretz and his wife, we were there for like half a day, and we brought all our stuff on one truck and we were gone because it all fit together and was prefabricated and super light. And a lot of the other installations, like without naming names, like are there the entire week setting the things up. And so I think that it is like in some ways like it raises a lot of questions about sort of extreme prefab and the benefits of that. Another really cool thing that we did then after that is that we still have material left over, but we made like another set of 30 tubes over the summer. And when we did that, we can dry them outside because it's super dry in Oregon and it doesn't rain. And it actually works better outside. So we have these laid out for like about a week in the backyard of Emerson, and they actually curve with much more consistency in the natural environment. And I just want to like end by saying that like when we go back to the idea that we could like basically flat pack an entire structure, this is the stack of these 30 tubes in its condensed state. And this is like it's like a little more than twice as much as what the amount of tubes that was used in the structure at the Mass Timber Conference. So we're talking about like flat packing like an entire structure into like a stack of plywood that's like this thick, also that our REU student can carry around. So there are like a number of key takeaways, and we're using this small project also to hopefully pursue manufacturing and larger tests on these including also partnering with a group in Germany for like using the photos that we took during the manufacturing rounds to try to inform and like teach and build up like hybrid data for training a model for predicting the curvature better. And yeah, we have an MS student that's also working on continuing this work. So a huge thank you to all the people that have supported this as like a small project, and especially to our students that really like push this through, and to Freres for also donating their time and like expertise from the supply chain side. Thanks. And I'll also say that we, in the spirit of reuse, we've reused the parts of these to develop this costume. And yeah, so if you come to my studio in Eugene, you have to wear this, as Michael Gershfield has has shown.
I refuse to put it on.
And also that the duck is a big fan. So thanks.